We'll now go to the second presentation, which is going to be done by Kumar Allady, and he will kind of go along the same topic that Mary was covering. So, Kumar, the floor is yours. We can see your screen, Kumar, but we cannot hear you yet.
All right. Thank you very much. Good morning, everybody. Thanks to Gerald. Thanks for the kind introduction. As my presentation is going to build into what Mary has said in terms of how can we increase subsurface characterization, and also can we obtain the benefits of risk reduction? Can we improve the quality? Can we also have a accelerated project delivery along with cost savings, both in terms of labor and material? And what I'm going to present today is a case study. Yes, we can get subsurface characterization. Okay, the case study is in Northwest 87th Avenue. The project is located in Miami-Dade County in Florida. It's a small bridge, approximately 130 feet long, and it's a three-span bridge. The foundation design consisted of 24-inch square pre-stressed concrete piles. The total number of piles the bridge was designed for 105, which included 6 test piles and 99 production piles. And the foundation design primarily consists of minimum tip elevations between -23 and -28. Basically, the design is governed by the lateral stability of the piles. So if you look in terms of the pile data table it was designed for a resistance factor of 0.65, basically coming with the drive 6 test piles and come with the driving criteria, and to drive the remaining 99 piles. So what you can see is in the RF value was 0.65, and the nominal bearing resistance is on the order of 145 to 160. But if you look for structural capacity for a 24-inch pile, the structural capacity for a 24-inch pile in Florida is around 450 tons. So we are not really utilizing the total capacity of actual capacity. So looking at the borings and the foundation layout, there's the layout of the 105 piles. What you have is 4 bends, end bend 1, intermediate bend 2, intermediate bend 3, and end bend 4. And like any project, you have typically, the borings are performed well in advance, so they're not along the alignment at the foundation. So you can see that 4 borings, or the sampling was standard penetration test, and you can see the borings depth varied anywhere between 30 and 75 feet. And the borings were spaced approximately 21 to 29 feet away from the alignment of the foundation elements, which is in this case pre-stressed concrete piles. And also what you see is the red circles are the test piles. There were 6 test piles proposed in the original design. Basically two test piles at the 2 extremes of end bend 1 and 2 at end bend 4, and 1 test pile each for intermediate bend 2 and intermediate bend 3 in the canal. So it's looking at the soil profile for the borings B1 and B2. What you can see is a typical Miami hard limestone right on the surface, and you have intermediate layers of sand. So what you can see is there are a couple of hard, again, soil profiles for boring numbers B3 and B4. And what you can see is a limestone right away, hard driving conditions. Right here on B3, you can see a 67 blow count, 82 right on the surface. And as you go deeper, you have some hard conditions like, and if you look at B4, around 50 blow counts per 1 inch of penetration. So basically, there's enough actual capacity in terms of the soil profile is concerned. So when the job was designed, so when we got involved, the project was already won by the contractor, and what we proposed, we did a value engineering on the job, and basically 2 changes we made. One is let's do 100% testing instead of 10%. We said let's do 100% testing, and let's use embedded data collectors. So what was impact in terms of the 100% testing was basically the resistance factor changed to 0.75. But at the same time, the contractor, because we are so late in the game, he didn't want to, like I said, the structural capacity for 24-inch pile is 450 tons, but we are using only nominal bearing resistance in the range of 142 to 139 to 150 tons. So he didn't want to reduce the number of piles. So we kept the same number of piles, but we optimized a little bit on the lengths of the piles. So we really did not take the benefit of the RF because of the schedule issues. So on another thing what we did because every pile is going to be tested, we said we proposed to do 4 indicator piles instead of test piles. We said 4 indicator piles. We removed the test piles from the intermediate bends because each pile in this case was 105 piles. All of them were going to be tested. So every pile was kind of a test pile. But what we drove was 4 indicator piles. You can see the 4 extreme corners of the project layout. Boring pile number 4 and pile number 26 for end bend 1, and pile number 2 and pile number 24 for end bend 4. So these were indicator piles. The savings sum comes with respect to the indicator piles, and the test piles was basically test piles when is in terms of schedule. Another thing is typically most of the test piles in Florida, you have extra 15 feet of driving length. So basically we saved some of the little the time as well as short lengths on the piles. So this was a 4 indicator piles how the driving was. So typically what you see is end bend 1, and we had basically 418 of 2019, 419, 2018. You can see some of it's all 2018. So there's a typo there. So basically we have the 4 piles, indicator piles driving schedule. And the second element of the value engineering was 100% testing, and the second element was the embedded data collectors. So for people who are not familiar with EDCs, basically EDCs are nothing but embedded data collectors, sensors which are embedded in the pile at the tip of the pile as well as the top of the pile. And there's a wireless communication data transmission when the piles are being driven. So what is advantage, a significant advantage in terms of the instrumentation at the pile tip is you have a closed boundary conditions. Basically, you have closed boundary conditions. Therefore, the software, when you can calculate the damping for every blow during driving along with other parameters. So basically, what you get is unique and independent solutions. So if a pile is laid out flat on the ground, so what you can see in this picture is you have an instrumentation at the tip of the pile, at the top of the pile, and then flush is what you have as a data port, which communicates to your workstation. And another thing with respect to all of us, we are familiar with the external sensors, is what we do is we get the capacity, total capacity. Then we go back to the office and we do a signal match to get your tip and skin resistance. But in this case, because you have top and tip instrumentation, what you get is independent tip resistance and skin resistance. And we call that FDOT method, just like in top external sensors, you call case method. In case of EDCs, what we call FDOT method because of FDOT and University of Florida, they have the patent. So what you see in this method of analysis is basically you get independent static tip and independent skin resistance, and you add independent tip and independent skin to get your total capacity. So which I can illustrate in terms of in the next graph. Here it is basically we have bend number 3, intermediate bend 3, and pile 12. Typically, what you see on the top of the graph is your total capacity, which is shown by a black portion of the graph, and the blue, which is the tip capacity, and the orange is your skin capacity. So if we have only external sensors, what typically we see is just the black graph. So when we go back and run our signal match, we can see the independent tip and independent skin. So in this case, what you can see is with EDCs, what you're seeing is for every hammer blow on the pile, you're getting your independent skin and independent tip, and you can get your total independent total capacity. And one of the key things what you also see between the pink side of the graph and the gray side is your restrike. So this is your during the pink is their driving during the driving, and the restrike is 4 days later. So what you can see is right here at the restrike for blow number somewhere between 360 and 361, the restrike, because of the restrike, you have a significant gain in your skin. So you can see during the driving process, initial driving process, the skin is, you don't have much skin, but when you come to the restrike, you gain in skin. But it's also, you see that what in terms of is your drop in tip, but it is not truly drop in the tip capacity, because you have to look at the bottom portion of the graph where you have your energy what being imparted to the pile on the right hand side, right y-axis, and also you have settlement. So what you see right here is the energy what you have imparted during the initial drive, you are not really imparting here. So therefore, what you see in terms of is basically it's not the true tip has not been mobilized yet. So basically, what you see in this case is a true soil structure behavior. And because of that independent skin and tip, we can get for every boring, what you see is the spatial variability. So we could run analysis on every pile element. So if I want to look at my substructural characterization along my end bent one, so randomly I picked, because of the screen size, I picked pile numbers 3, pile numbers 11, pile numbers 18, and pile 25, which is round circles. And also what I have is I picked up the closest soil SPT borings, FB deep analysis from the borings of B3 and B4, and I wanted to compare that. So what you see here is that soil characterization along the entire alignment of end bent one. So what you see here is the black hashed line is your nominal bearing resistance, which is 284 kips or 142 tons. And the red hashed line is your minimum tip elevation of minus 23 feet. And what you see, the blue solid line is your FB deep analysis. For in this case, for pile 25, I'm comparing with the closest boring, which is B4 FB deep analysis. And your orange is your actual FDOT static load capacity based on the FDOT method. And what you can see here is you already have your actual capacity at minus 5 feet. But again, the job was governed by minimum tip. So what you can see is the actual capacity. So what you can see is like each of the driven pile is like a CPT boring. So you're getting your soil characterization at the pile location, the vertically. So if you can go back and look at, now I want to look at pile 18, it's a similarly, but I'm comparing now with, again, the closest boring, which is SPT boring B4. And similarly, I can do that for pile 11, and with the closest boring FB deep analysis of boring B3, you can see the graph. Now, if I want to go and pick, now I said, let me go along what's the soil subsurface characterization along my intermediate bent number 2. Here, I picked randomly again because of screen size limitations. I picked up 4 borings, piles 3, 9, 15, and 24. And then I'm comparing with the nearest borings of B3 and B4 FB deep analysis. And that's what you get here in terms of the profile. So similarly, I can do that for, now if I want to pick for intermediate bent number 3, here I picked randomly another 4 piles. And now I'm comparing with the closest FBD boring analysis of B1 and B2. So what you can see is you're doing a design validation. What I'm doing is a complete design validation of my entire project here. So you can see borings B2, I'm comparing the FBD analysis of borings B2 with piles number 24 and 14, and B1 with pile numbers 9 and 12. Now, if I want to do what is my subsurface characterization along end bent 4, here I randomly pick 4 different piles, 3, 11, 16, and 23, and I'm comparing with the VDP analysis of B1 and B2. So again, you can see that. Now, once I've done along with alignment of the foundational alignment, now I want to look at, can I look at something horizontally? So here I'm picking across the job. So I'm picking pile number 7 from end bent 1, and pile number 3 from intermediate bent 2, and pile number 2 from intermediate bent 3, and pile number 3 from end bent 4. Now I'm comparing with the closest borings B3 and B1. So I can do that. So I can see the entire substructure characterization. And now if I want to pick another layer, I can cut across. Because I remember every pile has been a tested pile. So for every pile, you have your independent skin and tip for each blow of the hammer blow of the pile. So you can do that. And here's another profile for cross section for if I want to look at the bottom of this thing. One thing I want to also guys look at it is here along this canal embankment, you have a sheet pile wall, complete sheet pile right here along this canal. So I'm going to come back to that later. What's one of the advantage of what is the advantage of subsurface characterization? So here is the subsurface characterization cross section at the bottom layer of the foundation layout. So what does this mean? Basically, what we saw was when the job was originally bid by the contractor, the design quantities was 813 cubic yards, and because of the subsurface characterization and reduction of number of test piles from 6 to 4 indicator piles, and what we drew for the initial end bends, the contractor was driving at the rate of 3 to 6 test piles a day, because 6 piles per day. So we stuck to that kind of schedule, and then we, based on the information what we got along the alignment of the entire profile for the end bend 1s and end bend 4, we optimized and saying that, you know what, this is the length what you need for intermediate bends 2 and 3, which were inside the canal. And for one of the bends, we drove all the 26 piles in a single day. So because of that, what we had was the actual quantity of the piles reduced by 665 yards. So there was a saving of 147 cubic yards because of the extra subsurface characterization and the technology. So that was 18% reduction in terms of the quantity, which is a less carbon footprint because of the concrete. And also the design quantities were around 5,488 linear feet, and the actual quantities were 4,490 linear feet. And the cost savings purely based on that material savings, because the contractor bid at $115 per linear foot. That corresponds to $114,770. But also, if you take consideration of the instrumentation, which is embedded, the cost of the instrumentation was approximately $100,000. So if you really compare it with that respect to, the cost of the instrumentation is $100,000, but the savings is only $114,770. So is the savings totally only $14,000? To answer that question, let's look at the third element. When the planned construction was 30 days, but actual construction took place in 18 days because we could drive piles like 26 piles in a given day. Every pile was tested for every blow, right? So we had early completion of 12 days. So the real cost savings, what you're coming is based on operational costs. If you look at the pile driving, the contractor had $115 per linear foot, which includes his casting costs, transportation costs, and your installation or driving costs. So if you eliminate, on those 4,490 linear feet, and you have operational or installation costs have been reduced by 12 days. So if you have saved $1 on operational costs or driving costs, for every dollar, you're going to save around 5,000. So what I'm trying to say is, in actual quantities were 4,490, because if you have early completion, the contractor saved $10 per linear foot, then the actual savings is around $45,000. Do you add? So that's the true savings are a lot more than based on the material savings what you reflected here. So basically, once you meet all the three elements of your people, which is your early completion, safety and early completion, and the planet, which is your carbon reduction, and the money's economy or the profit. So you meet all those three legs. So therefore, you can call that project as a sustainable project. So typically, the savings, when we say operational savings, and when we talk about where the savings comes with the technology, what we have realized is the savings comes from 11 different silos. And one of the silos is higher resistance factor. In this case, as I said, we could not utilize, there's not much savings in this particular case study with respect to higher resistance factor. The second savings is improved site characterization. As I've shown that we have site characterization for the entire project. Where does the savings come in is, I've shown about this, I talked about the sheet pile wall along the canal alignment. So when the contractor was driving the sheet pile wall, there were a lot of hard conditions as I've shown in the profiles. So the contractor had a change order. So when the change order came to the owner and the designer, at that time, the decisions were made based on the data. Now you have the subsurface characterization along the entire end bent, along with the two borings on the canal bank. So they could make a better decision. Hey, this is a genuine change order. There's a different this thing or not. So you have additional information so there was indirect benefits on the project in terms of making decisions as well. When we talk about risk reduction for all the parties, whether it's the owner, the designer, or the contractor. And the third silo is elimination of external gauge setup time. And one of the things what we learned was when the contractor, as I said, the contractor initially for the initial bends, they were driving 3 to 5 piles per day. And then for one of the bends inside the canal, he drove 10 piles in a day. Then the last intermediate bend, they drove all the 26 piles in a day. And when we asked the contractor what kind of savings, he said because of external gauges, when we install and uninstall, for each pile, it takes half an hour. So when we are talking about 26 piles, just to install and uninstall, it's going to take half an hour, it's 13 hours. But within that 10 hours, they drove all the 26 piles because there's no external gauge installation, because the gauges are installed in the casting yard. And the fourth silo, what the savings came was with respect to operational savings is the cushion changes. The Florida DOD specs you have to change the cushions when the cushion after a certain number of blows on a pile, or the cushion thickness is reduced by half. But in this case, because the instrumentation is inside the pile, you are measuring the true stresses for every blow, whether the tensile as well as tensile as well as compression stresses, and you are comparing with the actual allowable structural stresses. So therefore, you don't need to change cushions arbitrarily. You can make the cushion changes based on the actual stresses on the pile. That's one. And the fifth silo was the C2QP inspector, because it was the job was a design bid build job, and once you do a value engineering in Florida, it becomes a design build project. When you become a design build project, they have multiple people to inspect on the job. Along with the dynamic testing engineer, they need a C2QP or certified C2QP inspector. So because you're making decisions based on the data driven for every blow, so you don't need multiple people. So there was one reduction in staff. You have only one inspector from the CEI and one dynamic testing engineer from the contractor. You don't need another inspector from the contractor. So there were savings in terms of here. There were savings for both the owner and the contractor. Elimination of unplanned restrikes, not applicable to this particular project. Elimination of overdriving. In this case, what we see, limestone was very hard conditions. Since you have the tip instrumentation, you are measuring the actual stress of the tip of the pile, so you are basically eliminating pile damage, which is basically, again, when I talked about the originally, can we improve quality of what we are giving the product? So in terms of your elimination pile damage, so there was by overdriving. So reduction in unused pile length. One of the things what I said, we optimize like any other project as we go, as we learn from one bend to other bend when you're driving. So you are optimizing your length. So therefore, you're eliminating your wastage of your material. Elimination of splicing, not applicable for this particular project. Reduced high strain dynamic testing engineering cost. Like I said, if originally the project was planned for 30 days construction, now you reduced it to 12 days. So you have 18 days less personnel in the field. And plus, when we talked about the method of analysis, it's a single step. You're not doing a two-step. You're not going back and doing a signal match. Here you are getting your automatic signal match for every blow. So you have is a robust criteria, robust analysis. It's a closed-end analysis because your boundary conditions are well defined. So therefore, the savings are coming from that. What are the additional benefits? There was one of the additional benefits, I said, one with respect to sheet pile. Another thing is another additional benefit was for this particular project, since the sensors were installed in the casting yard, we were doing the monitoring concrete curing in the casting yard. So we were also measuring the stresses when the piles were being transported from the casting yard to the project site. So you have this additional quality control during casting, during your transportation. And also, this bridge is one of the bridges which, for some of the piles in each bench are being repurposed for life cycle monitoring, so that you can see what does it mean is in terms of the additional benefit is when in the future the DOT wants to widen the bridge, they can see how much availability is there in terms of that, and also this is a future ready bridge because it can communicate in cloud with the driverless cars or some of that. So basically foundation load rating is possible. So those are some of the additional benefits what we have in terms of this. I know we are short on time, so I have a couple of videos. I think the PDF will be shared with every this thing. There's a productivity video. You go to EDC productivity video on YouTube. 26 piles being driven a single day, and also you have another video called Life of a Smart Pile. With that, thank you, Gerald.
Thanks, Kumar, for your presentation. It's on a similar, along the same lines as Mary initially about increased subsurface characterization, how that helps, and then at the same time, again, looking at an innovative way to get more data from just basically monitoring every single pile.